So first of all, if I say just divide 5 over 5, how much do you get? I'm just slowly going to that.
1.
1. 5 over 4. Oh, sorry.
1.25.
I think I'm going the wrong direction. Go this way. Yeah, 5 over 10. Yeah, so you get half, right? Okay, then how about dividing it by 100? You get this, right? Okay. Now, if I divide it by 10,000, what happens? You get 0.005. Do you agree? So as you can see, our denominator is getting bigger. I mean, we're dividing 5 by a bigger number, and our value is actually on the decrease. It's getting lower and lower, right? Can you see that? So that means if we increase the denominator, the overall value will be getting slowly and slowly will be getting lower, will be going towards 0. Can you see that? Because it's really small, right? Like if I divide it, what happens if I divide it by 1,000,000? What if I divide by 1,000,000? You'll see it will be really small. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you'll see the value is really small. Okay. So since we are dividing it by a bigger number, the value is getting smaller. So if I divide it by something really big, say infinity, what do you think it would give us? You can't
Something
really
close to
divide.
0.
Yeah, exactly. You can't really divide anything by infinity, to be honest. That's true. But you can imagine a really big number. That's why I have instead used infinity, to show that we are actually considering something really big that we can't even write down. Okay, let's say we have 1 trillion zeros after 1. So you can see it will be almost 1 trillion, less than 1 trillion zeros than 5 here, right? If we divide something by that, something by 1 trillion zeros. So 1 trillion. So you can see the value is really small. You can actually say that, hey, there is no real value. It's actually a 0. That means as your denominator gets bigger and bigger and approaches towards the mega infinity, towards a very big number, your value actually approaches to 0. Do you agree?
Yes.
Anyone who is still confused why it is approaching to 0? Anyone? Or does it make sense, make more sense perhaps? If it makes sense, then now I can show the third property, which is limit x tends to either it's positive or negative infinity. No problems with that. If we have x to the negative n, let me start with the first one. So I can rewrite 1 over x to the n as x to the negative n. Limit x to the infinity, x to the negative n, oops, sorry. X to the negative n. So this guy will approach to 0. Now let's use this idea of y. So if I start with this one, 1 over x to the n, 1 over x to the n. So as your x is reaching or rather approaching towards infinity, this denominator will get bigger and bigger, right? You know, it will approach to infinity. That means if x approaches to infinity, that means x to the n also approaches to infinity, right? Because it's just the exponent. Whatever the value of x is, the exponent is actually the exponent actually gives you a bigger value, don't it? For example, if x is 5, what does x squared gives you? It actually gives you a bigger value. So if x tends to infinity, x to the n actually is a bigger value than that. Doesn't matter what your n is, whether it's odd or whether it's even, doesn't matter. It will actually give you a bigger value. And there is, you can't really say that we have twice the amount infinity. Anything bigger than infinity is still infinity. You can't really define anything beyond that. So it says x to the n also tends to infinity. Now, again, we have seen that if we divide something by infinity, I mean a really, really big number, you guys agreed with me that the value actually goes really, really close to 0. So instead we can say that, hey, let's say that it's a 0. So this is the same here. We are dividing 1 by a really, really big number. Or in other words, I can say I'm dividing it by an infinity. So it will take me to 0. Do you agree?
I have a question.
Sure.
What happens when we have like infinity over infinity?
That's completely undetermined. We can't really determine anything. That's not undefined. We say that's undetermined. That means we can't determine or can't say anything about it. That's a good question. It means we still don't know or we still can't determine anything mathematically when you divide infinity by infinity. If we add infinity with infinity, we say that will still give us infinity. If we multiply infinity with infinity, we still say that will still give us infinity. But when we divide infinity by infinity, then we can't really reach any conclusion mathematically. That's why I say it's undetermined. Can't really determine this value. Okay. Any question from this? I guess it's number 3 from 2.6. If you see that I'm not really responding to the chat, please unmute yourself. Okay. It's difficult to keep an eye on both the devices at the same time, but I'll try. But if you see that I'm not responding, please unmute yourself. Okay. Let's go for the next one if you don't have any question. So Number 4. Says limit x tends to positive or negative infinity. I think I should have positive or negative here because it's true for either of those infinities. Okay, so if you have a polynomial, this p of x signifies a polynomial. So if you have a polynomial, let's say in this format, it will always be infinity, depending on the degree of the polynomial and the sign of the leading coefficient an. Okay, now what does that mean? Let's try an example. Then it will make more sense of it. So let's try this one. Let's say we have p of x equals 3x to the 4. Let's try this one. We'll try to avoid the other parts because it will be more difficult to understand with the additional part to it. Let's try this one only. 3 times x to the 4. Okay, and if x tends to infinity, what happens? Can you tell me? Limit x tends to
The whole piece goes to infinity.
limit x tends to infinity for 3 to the x, 3 times x to the 4. Okay, so first of all, we can using the limit law of constant multiple, we can keep it outside, right? We can keep the 3 outside, and then we can see the infinity will actually act on x. And since we have a positive exponent, and x is approaching to positive infinity, so we don't really care about the exponent, whether or not it's even or odd. We only care about where it's now taking us to. So if you plug in infinity here in place of the x, you can clearly understand x to the 4 will give you a bigger value. So what's infinity to the power 4? That means if you multiply infinity 4 times with each other, what does it give you? It still gives you infinity, isn't it? So, and then you are multiplying infinity by 3. So infinity times anything, I mean, if you multiply the infinity by anything or with anything, it will still be infinity. So the resulting value will be infinity. Do you agree? So now, let's see one more example. I think we'll need a couple of more, not only one. Let's see, let's say now I have another polynomial, which is 6x squared, negative 6x squared, let's say. Let's say I have another polynomial, negative 6x squared, okay? And now again, I'll keep this negative 6 outside using the constant multiple law. Now I know x tends to infinity for x squared. Again, if x is approaching towards infinity, x squared will also approach towards infinity. Do you agree? Because the exponent actually gives you a higher value, and we can clearly assume that any higher value of infinity is still infinity. Now, if you multiply it by a 6, it will still be infinity. No doubts on that. But what happens with this negative sign? Can you imagine anything?
Will it change it to negative infinity?
Exactly. This negative sign will actually take you to the negative infinity. Sorry. Can you imagine why? Because this negative sign significantly says, or rather signifies, I would say, that your function is decreasing. How far can it go when it's decreasing? It can go up to negative infinity, right? So that's why in the statement they have said uh, it depends on, I mean, the sign of this infinity depends on the degree, that means n, depends on the degree of the polynomial, which is n, and the sign of the leading coefficient. Now, what is a leading coefficient? Leading coefficient is the coefficient of the term with the highest exponent. We have several. We can have several coefficients, but we only care about the leading coefficient. We are considering only one term here. So the leading coefficient is of course -6. But if we have more than one coefficients like this one, 3 times x to the fourth minus 6x squared, let's say 5x minus 12. Let's say we have a polynomial like this. So the highest exponent, highest degree, highest power is 4. So the leading coefficient of this polynomial will be 3, positive 3. We still have other coefficients, that is -6 plus 5, but we only care about the leading coefficient. On this occasion, we are only considering one term, so the leading coefficient is -6, and the sign of this leading coefficient is negative, so it will take us to negative. Do you agree? And so this tells us about the sign of the leading coefficient, sign of an. Why does it tell us that it also depends on the degree? That means the highest power, highest exponent of the polynomial. Can you imagine anything? Why it's saying that it depends on the degree of the polynomial? Anyone?
Repeat the question.
Yeah, sure. So the fourth statement says the sign of infinity depends on the degree of the polynomial, which is n, this n, or this n, this is the same, literally. The degree, that means the highest exponent of the polynomial, highest power of the polynomial. And my question is, why should it depend on the highest power? Why should it depend on the degree of the polynomial?
Because if it's to an even power, it would be positive. But if it's to a negative power, I mean, to an odd power, it would be negative.
Very good. So when x is approaching to negative infinity, then this n will have something to say. If it's approaching to positive infinity, it doesn't really matter. It will still take you to infinity. But if x is approaching to negative infinity, then this um, degree of the polynomial, or the highest power of the polynomial, will be um, significant, because if n is even, when n is even, an even power always makes anything positive. You can't have anything negative when you have an even power, right? So if n is even, your x to the n will tend to positive infinity. Even though x is approaching to negative infinity, still x to the n will approach to positive infinity. But if n is odd, then it will approach to negative infinity. Do you agree?
Yep.
That's why it says that the sign of the infinity, Brody entered the waiting room. Okay. The sign of the infinity actually depends on the degree of the polynomial. That means the highest power of the polynomial, highest exponent, and the leading coefficient. That means if you have any coefficient uh, with the highest power of x, it could be 1 anyway. It could be 1. If it's 1, then it's not a problem. But if it's negative, then it might change the direction. So you need to see the sign of the leading coefficient, not the other coefficients, by the way, only the leading coefficient. That means the coefficient um, associated with the highest power of x. Okay. Any question from this? No questions at all? All right, let's move on then. Next, we have okay, next we have the slant asymptote. So it's the figure 2.41. It's the slant asymptote. Can you eyeball and say, how can you define an asymptote like that? You don't need to find or look for any bookish definition. You just need to imagine what's going on here. Anyone?
You said for a slant asymptote?
Yeah, why do you think, or rather, maybe I can say, how can you define a slant asymptote? You know, if you, or let me start
Could you
sharing.
define it with some type of like functional equation, since it'll have, I don't know, since it wouldn't just be vertical or horizontal, wouldn't it have both vertical and horizontal direction since it's slanted?
Okay, so this is, okay, yeah, this is figure 2.41, and they're saying that this diagonal line, not really diagonal, I should say opposite diagonal line, is a slant asymptote. So
when the degree of numerator is greater than the degree of denominator.
I couldn't understand what he said. Would you please repeat it?
When the degree of numerator is greater than the degree of denominator, that's slant asymptote.
Oh, you are saying that, I understand. You are saying the algebraic requirements for it. I understand. Yeah, but I'm trying to get the information graphically. I mean, why they're saying that this should be an asymptote? I mean, obviously, there is no real line in a graph. We actually draw this ourselves to show that the graph is actually not going beyond this, right? If you draw any graph, you actually don't have this type of asymptotes. Not only slant asymptotes, you actually don't have any vertical or horizontal either. We actually imagine this because we can see that the graph is not going beyond that imaginary line. That's why we use dashed line. And we show that, hey, when we have this function, the graph of this function doesn't really exceed this line. So same goes with the slant asymptote as well. If you remember, for all the vertical asymptotes and most horizontal asymptotes, we have some exceptions. We have seen that the graph don't really cross. The graphs don't really cross, or neither touch it. Forget about crossing. It doesn't even touch the imaginary line, and then we say that it's an asymptote. So same goes for slant asymptote as well. When you draw this graph, you will see that if you have an imaginary line here, doesn't matter what value of x you take, it will never touch nor it will cross it. So if you have an asymptote like this, which is neither vertical nor horizontal, you can say that it's a slant asymptote. That's the most naive definition though, but you can clearly remember this way. Okay. All right. Let's see the algebraic requirements. We have already seen how does it look like graphically. Now we want to see what happens algebraically, or how can we calculate the asymptote, how can we find the asymptote when a function or a polynomial is given. Okay, it could be a polynomial, it could be a rational function, whatever. If a function is given, now we want to know how can we calculate or how can you find the asymptote. Okay. All right. So you will need to remember these 5 categories, because you will see some questions where the graph will not be there, only the function will be given, and still you'll be asked to calculate the asymptote. Okay, it's really easy. It's super easy. I'm telling you. But having said that, it's tricky as well, because you can see you need to remember all these 5 and see which one is actually matching with the given function. Only one can match, to be honest, but you have to cross check the requirements, right? Okay, now let's see how can we find it. And oops, I think I have something in the chat. Will there be homework problems on this and resemble the exam questions? So it's still we're still on 2.5, so I believe you will see questions like this in the exam, definitely, because the exam will cover up to 2.6. So I assume that you might see a question like this. Obviously, there won't be a question from each of the topics. We have already seen several topics, but I assume you'll see a question like this, because it will be super easy, as I said. You don't even need any calculator, or you don't even need any scratch work for it. You can just eyeball it and excuse me, and draw the conclusion, as long as you can use it perfectly. You can use it the right approach. Okay, now let's say we have a function. We have a function in the form of px over qx, where both of these are polynomial, and these leading coefficients are not 0. That means, obviously, we have an exponent of x. It's not a constant function. This am and bn is not 0. That signifies that we definitely have something with x. It could be 1, no worries with that. I mean, m or n could be 1. That's still fine. But we need to have x. We need to have at least something with x. It can't be a polynomial. Okay. Now, let's see what are the requirements for each of those. So if m is less than n, then y equals 0 is the horizontal asymptote. Now, what is our m and what is our n? We just need to eyeball it. So m is the exponent, highest exponent, or we say the degree of the numerator. And n is the degree or the highest exponent, highest power of the denominator. Okay. So if you see a function, I'll show one example of each, no worries. But let me go over this first. So if m is greater than n, if m is less than n, that means if the degree of the numerator is less than the degree of the denominator, then we say we have a horizontal asymptote, and the asymptote is y equals 0. Okay, I think I should start showing the examples. Yeah. Again, I'll start sharing the screen of my iPad. So I want you guys to please have the slides open. Okay, so that you can see the screen, what I'm sharing, and at the same time you can see what the requirements are saying. Okay, so the first one says if m is less than n, then obviously the function.
Okay, I'm gonna have you on this.
Can you unmute yourself? Okay, I have muted you. Sorry about that. So if you have any question, you just unmute. You can just unmute yourself. All right. So obviously the function will be heading towards. Oops, sorry. Of course, will be heading towards 0, and we have an asymptote, horizontal one though, which is y equals 0. Okay, now let's see an example of it. So let's say my function is f of x equals to x squared plus 5x minus 3. And in the denominator, I have x cubed minus 1. Let's say this is my function. So I don't even need to calculate anything. I can see the degree of the numerator, that means the highest power of the numerator is 2, and the highest power of the denominator is 3. And I know that if the degree of the numerator is less than the degree of the denominator, which is on this occasion true because 2 is less than 3, definitely less than 3. So straight away, I can say, hey, when limit x tends to positive or negative infinity, which way, it doesn't matter. Obviously, the question will have either positive infinity or negative infinity. So the question will have something like this. What happens to the limit? You can straight away say the limit is 0. You don't need to calculate anything. You can just use this property or theorem, I should say, and say that limit for this particular function when x tends to infinity or x tends to negative infinity is going to be 0. If the second part of the question says, where is the asymptote? What kind of asymptote is that? You can straight away say we have a horizontal asymptote, which is at y equals 0.
So
0 is the horizontal asymptote. Yeah, go for it.
for the horizontal asymptote, the power in the numerator has to be less than the power in the denominator?
Yep. We can still have horizontal asymptote, but it will be a special case. It will be the horizontal asymptote will be y equals 0. It will always be the case whenever the power, not only power, I should say the word degree, that means the highest power of the numerator is less than the highest power of the denominator. Whenever you see this case, and if x is approaching towards infinity or negative infinity, obviously you'll have a horizontal asymptote, but it will always be y equals 0. Doesn't matter what the function is. You'll still see some horizontal asymptotes, of different format. But if this is the case, that means if m is less than n, the horizontal asymptote will always be y equals 0. Okay, and you can see we don't even need to calculate. We can actually just eyeball it and draw the conclusion as long as we remember it properly, right? We can see 2 is less than 3 and x is approaching towards infinity. Obviously y equals 0 will be the horizontal asymptote, right? Any question from this? Anyone? Any question? No questions at all? Okay, let's move on then. As I said, it will be super easy. You'll find it really, really interesting. Obviously, as long as you can use it properly, because you need to remember 5 of these, and the margin for error is really, really small, because if you get it wrong, you'll get a 0. There is no possibility of getting a partial credit for this type of problem. That's the other side of the coin. It's super easy. That's why you will get, most of you will get full credit on this. But if you somehow miss it, if you somehow don't use it properly, then you will get penalized. So that's the problem anyway. Let's see the next one. So number 2 says if the degree of the numerator is equal to the degree of the denominator, that means if m is equal to n, then we say that whenever x tends to positive or negative infinity, our function will approach towards a to the m over b to the n. That means the ratio of the leading coefficients. The ratio of the leading coefficients. Okay. And what about the asymptote? Y equals, again, the ratio of the leading coefficient will be the horizontal asymptote. Okay. Now let's see one example of it, and then hopefully it will make more sense. So let's say my function is squared plus 3, and the denominator is x squared minus 5. Okay, that's my function. So the highest power of the numerator is 2. The highest power of the denominator is also 2. You can see it satisfies m equals n. think I should add some coefficient here. Let's say 4 and 3. Yeah. So again, let's go back to the exponents. The degree of the numerator, or the highest power of the numerator, is 2, and the highest power of the denominator is also 2. So that means they are equal. And when that's the case, we say the function, when x tends to positive or negative infinity, the function will approach to the ratio of the leading coefficients. So the ratio of the leading coefficient is 4/3. And also y equals, oops, sorry, I think I should use the white color. Sorry about that. Y equals 4/3 is the horizontal asymptote. Do you see how easy is that? As long as you remember it. Just take the ratio of the leading coefficients, which is 4 and 3 on this occasion, right? Any question from this? Anything that you can generate by just observing the discussion? All good? Okay, let's go for the next one then. The third one says, when the degree of the numerator is greater than the degree of the denominator, that is, when m is greater than n, then the limit when x tends to positive or negative infinity, the function will approach to positive or negative infinity. I should write or, otherwise you might, when you rewatch it, you might think that I'm dividing it. Yeah. Okay, and we say that that function has no horizontal asymptotes. Okay. Now you might be wondering, why do you have positive or negative infinity? So it will again depend on the function itself. You will see some function will tend to positive infinity, and some will tend to negative. So we'll see examples of those. Uh, if you can't do this today, you'll definitely see some in future. So no worries. But if you remember that whenever m is greater than n, the function will eventually approach to either side of the infinity and will not have any horizontal asymptote. You can clearly imagine if the function is approaching towards infinity or negative infinity, we can't really have an horizontal asymptote, that's for sure. Because an horizontal asymptote looks like this. Right? Or it could be here, above the x-axis. But if your function is approaching towards positive or negative infinity, either this way or this way, you can clearly imagine we can't really have an horizontal, or can't really have a horizontal asymptote, right? Because it will definitely cross the line, whatever we have, because since it's approaching towards infinity or negative infinity. So there is no way you can have a horizontal asymptote, that's for sure. Okay, let's see one example of this as well. All right, so let's say our function is x cubed over 2x squared minus 1. Let's just take this one. Now again, the degree of the numerator is 3, and the degree of the denominator is 2. So clearly m is greater than n, and if m is greater than n, we know there will be no horizontal asymptotes, that's for sure. And when x is approaching towards either side of the infinity, this will definitely approach towards infinity as well. Okay, and on this occasion, it will approach to positive infinity. But we don't really have anything negative in the leading coefficient. Okay, all right. Any question from this one?
I have a
Yeah, sure.
so on for like the test, if we had one of those where there's no horizontal, will we just type in no horizontal asymptote?
So if you are working on a problem which has an answer box or show your work or upload your work place, then you can definitely type or write down. But if you're doing it for a multiple choice question, there will be options like this. Yeah, you just need to select which one satisfies your uh, categories or category, I should say. I think I'll give it as a multiple choice question because it's a really smallish question. It shouldn't take more than 10 seconds to see what's going on here, because just you can eyeball that 3 is greater than 2, and there is no horizontal asymptotes. That's it. It shouldn't take more than 10 seconds. So I think I'll go for the multiple choice question again. But yeah, if there is any show your work or upload your work place for that question, yeah, you can write down or type it. Okay, someone is in the waiting room. Okay. All right, let's take a break for 5 minutes. At 10:12, we'll meet again and start from number 4. Okay. Okay. So number 4. Any question up to 3, by the way? All good? Perfect. Number 4, or theorem 2.7D. This is technically 2.7D, okay? If you're wondering which one is that. Okay, so it says when m is exactly 1 more than n, exactly 1 more than n, then we say that f has a slant asymptote, okay? And the function, again, will either approach to positive infinity or negative infinity. Or negative infinity. When x approaches to either side of the infinity. Okay. Now let's see that. So let's say our function, I think we have already seen that. Yeah, in this example, I think we can use this example. Okay. Since m is greater than n, we did say that we don't have any horizontal asymptotes. But we can also see that 3 is basically just one more than the degree of the denominator. Can you see that? If the degree of the numerator is just one more than the degree of the numerator, which is true on this occasion, then we say, although we don't have any horizontal asymptotes, but we do have a slant asymptote. Okay. So again, you can cross-check whether or not you have a slant asymptote whenever you can see that there is no horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, you will conclude that there is no horizontal asymptote. The next thing you want to check is whether it's just one more than the degree of the denominator. If it's just one more, then you can say that we have a slant asymptote. Otherwise, we'll keep saying that there is no horizontal asymptote. That's what we can derive from the given function. That's information we can derive. Okay. Any question from this one? No questions? Okay, let's go to the next one. Number 5 or 2.7, theorem 2.7e says how to find the vertical asymptote. Now we have finally reached the vertical asymptote, and this says in the reduced format, we just need to find the zeros of the denominator. I mean the zeros of the polynomial q. Whenever we have a function like this, p of x over q of x, and in the reduced format, what do I mean by the reduced format? Let's see. Let's say we have this x cubed plus x, and this is x to the 4th plus x. So the reduced format is, if we factor out 1x, we have this. If we factor out from the denominator, then we have this. So the reduced format is x squared plus 1 over x cubed plus 1. Okay, so this is the reduced format of this function. So we say in the reduced format, we just need to find the zeros of the polynomial q. That means whatever we have in the denominator. We just need to find the zeros of this. Now, a quick question could be, how can you find the zeros of any polynomial? Of anything, how can you find the zero? Anyone?
the degrees?
No, the degrees doesn't really give us the zeros.
You said you want to find the zeros, like where the function itself equals 0?
So when you are trying to, when I say that find the zeros of q, let's say q of x, on this
Oh,
occasion,
wouldn't you have to like factor it or something?
not really. Anyone else? This is the q of x we have. We're trying to find the zeros of this.
Would you set it equal to 0 and then solve for x?
Exactly. So it doesn't really matter what your polynomial or what your function is. You just set that to 0 and solve it for the variable you have. So when you say that find the zeros of q, so whatever you have in the reduced format, of course, whatever you have in the denominator, just set that to 0 and solve that for the variable you have. In most occasions, in probably 9 out of 10 problems, you'll see the variable will be x, so just solve it for x. Okay. All right, so let's try one example. Let's see, what should we do? Let's try this example. F of x equals to, let's say, x over x squared minus, x squared minus 1. Let's try an easier one. Okay, and I'm saying that, hey, can you find the vertical asymptote of this function? So what should we do? We should first see whether the function is in the reduced form or not, and definitely it can't be reduced anymore. But this one, we can rewrite it, but it's still definitely in the reduced format. Although we can rewrite it, we can use this formula and rewrite it as this. Again, that was still in the reduced format. You don't need to rewrite it though. Still was in the reduced form. So when it's in the reduced form, we just need to set the denominator to 0 and solve it for x. So let's do that. So we'll set the denominator to 0 and solve it for x. So that means either x plus 1 is 0 or x minus 1 is 0. Because when you have the product, when you have 0 as the product, at least one of these has to be 0. Otherwise, the product can't be 0. So that's why either this one is 0 or the latter one is 0. So if we solve it for x equals -1, x equals +1. So we say we have two vertical asymptotes. One is at x equals -1 and the other one is at x equals 1. There are two vertical asymptotes. Okay. So when I say find the vertical asymptote, all you need to do is to see whether the function is in the reduced form. If it's not, reduce it as much as you can. I mean, simplify it as much as you can, reach the reduced format, and then just set the denominator to 0. You don't need to see the exponents, I mean, the highest exponents or the degree of the numerator and the denominator. You just set the denominator to 0 and solve it for x. Okay. Any question from this? No questions at all? Okay, now we have all the 5 uh, parts of the theorem. So clearly, you can see this is really easy. This is super easy, especially when you're trying to calculate the horizontal asymptotes. Then you can just eyeball it and calculate. For the vertical one, yeah, you might need some scratch work and all that. But for the horizontal ones, you can just eyeball it. But you can also see that it's tricky. It's really easy to make a mistake. If you just forget what happens when m is greater than greater than n, what happens when m is equal to n. If you just mix it up with any other category, then you'll get a different result, and which will be wrong. Okay. All right, let's move on then. Let's move to the next slide, which is the end behavior, theorem 2.8. Theorem 2.8. So now we have theorem 2.8, and it will give us an idea of the end behavior of e to the x and e to the negative x and natural logarithm of x. Okay, and you can remember it for the shortcut because it will save your time. You can also imagine this if you know how does the graph look like. But if you want to save some time, maybe you can remember this. It will definitely help you in the long run. Okay, so the graph of e to the x, let me draw it for you. The graph of e to the x looks like this. Okay, and the graph of the natural logarithm looks like this. Now we want to see the end behavior of this. So when x tends to positive infinity, that means we are approaching to our right. This is going to positive infinity. Do you agree? I think I should use the arrow here. Yeah. This is going upwards, and I can't see any end of this. So it will actually go towards positive infinity. Do you agree? So we say the limit of e to the x when x tends to positive infinity is infinity. Okay. All right. What happens when it's approaching to negative infinity? When x tends to negative infinity, what happens? Don't look at the theorem. Just try to eyeball it, eyeball the graph, and try to see when you are approaching towards negative infinity in this direction. What do you think? Where do you think function e to the x is heading towards? Anyone?
Negative infinity as well.
Negative infinity.
Not really.
It looks like 0.
Yeah, 0, because negative infinity is actually in this direction. This is actually heading towards this particular line. Oh, sorry, I think I should use a different color. It's actually heading towards this line, right? This greenish line is actually heading towards this line, and this line is actually 0. This sky blue color is actually where x is, sorry, y is 0, because that's the x-axis. So you can say that it is heading towards 0. Okay. Let's see natural logarithm of x. Again, we'll be going to positive infinity this way. Okay. And the positive infinity, I mean, when we are approaching to positive infinity, what happens? Which way do you think it's going towards?
Negative infinity.
Why do you think it's going towards negative infinity? It's definitely going to
It's
this
going
direction.
to be like a there's like a slant asymptote between the two. I guess it'd be going like between that. I don't know.
We have only one function here. Let's forget about the greenish one. We're just taking care of this one now. So we can see that it's going upwards, isn't it? It's not really stopping anywhere, or it's not really, I mean, definitely the function, I think my function is slightly wrong.
Okay, I think maybe it will be infinity.
Yeah,
Positive infinity there.
exactly, because it actually looks like this. That means it's actually going this way, up and up and up, right? So it's actually positive infinity. Yeah, very good. So when x tends to infinity, important ISS staff information, check it later, ln x, or natural logarithm of x, will head towards positive infinity. Now, for natural log or for any logarithmic function, our x can't be 0 or less, because we define logarithmic functions for values of x strictly greater than 0. If you plug in any value of x, which is 0 or less, in the calculator, for any logarithmic function, we'll see math error, because we have defined logarithmic functions for x strictly greater than 0. We can't have any value, any negative value, not even 0. You know, we can't have any negative value and 0 for any logarithmic functions. It has to be strictly greater than 0. That means when we can go, actually we can go up to this, we can go up to 0, but not exactly to 0. Okay, we can go up to 0, but not exactly to 0. And for that, you can see the function is going downwards, right? So we say whenever x tends to, x tends to 0 from the right hand side, natural log will head towards negative infinity. Now the most important part here is this. Why is that? Because as I said, we can't have 0 or less, but we can go up to 0 from the right, from this way, up to 0. We can't come from this way because we can't have a negative value. We can't have 0 either. We can go very close to 0 and see how does it behave. And we can go from the right side. So that clearly means it's the right-sided limit when x tends to 0, right? That's why we have a 0 plus. We have already seen what does this plus sign means, right? Any question from this? Any question? No questions at all? Okay. And similarly, for e to the negative x, you can also remember this for future references. For e to the negative x, let me use white color. Again, if you have problems with any of this color, please let me know, okay? We know that for e to the x, it approaches to infinity when x tends to infinity. So for e to the negative x, can you imagine anything? Because it's the negative exponent, or in other words, you can rewrite it like this. Where should it head towards?
Should approach 0, wouldn't it?
Yeah, it will approach to 0. Very good. Because we know that e to the x approaches to infinity when x tends to infinity. So anything over infinity, we know that's 0. So can you see how we can use this information in future, for different problems? And similarly, for x to the negative infinity, e to the negative x, or if I rewrite it, if you rewrite it, often it makes more sense. I used to rewrite it in the convenient form when I was in your place, because it makes more sense. So now we know e to the x tends to 0 when x tends to negative infinity. That means this guy tends to 0 when x tends to negative infinity. Then what it will give us for 1 over 0? Anything over 0, you can write infinity, right? So you can see we can use those to solve it pretty easily. We don't need the graph, we don't need any explicit calculation, anything at all. If we just know this, we can use it and find other significant results. Any question from this?
So for the denominator, is that saying x is approaching negative infinity? I mean, for the second one in the denominator, sorry.
This one?
Yeah.
Yeah, it's approaching to negative infinity, yeah. Any questions? Any other questions? All good? Okay, let's start 2.6. So yeah, I don't think I'm going to finish it today. So yeah, I think you have a good news. So 2.6 will not be in the exam. Okay. Since I can't finish it, I'm not going to add this. So your exam will be from 2.1 to 2.5. Because obviously I won't add anything which I haven't really shown. All right, so let's start 2.6 now. I'll make an announcement, no worries. So keep an eye on the announcements, especially during the weekend, of course. All right, 2.6. Now we want to find the continuity. or what does the continuity mean? Mathematically, how can we say that if a function is continuous or not? So first of all, I want you guys to tell me, what do you understand by this word continuity? Forget about the mathematical aspects of it. When you hear this word continuity, what do you understand? You know,
It's like
what
one piece.
uh one piece. Okay, yeah, I think we can take this answer. Again, just forget about mathematical aspects. What do you understand in English when you hear this word continuity? Anyone?
Continuity means never end.
Never end. Okay. Yeah, that makes sense.
A continuous like line.
Sorry,
A continuous line.
continuous. So what?
Like just something that continues.
Yeah, that's something continuous. Okay. So in maths, we have obviously certain criteria which a function needs to satisfy when you say that that particular function is continuous. Okay. Now, let's look at the definition first. I think I should start sharing the slide again. Here you go. Okay, so the definition says a function is continuous at a point A, where A is a constant, if the limit at that point is actually the functional value at that point. I mean, the limit at that point equals to the functional value at that point. That means in maths, we write this: limit extends to A, f of x equals to f of A. F of A is the functional value at A, right? We are saying that functional value of this function f at this value A, at this point A, is equal to the limit of that function when x approaches that particular point. Okay? Again, we'll see examples so that it makes more sense. But that's the bookish definition if you are trying to find one. Okay, now let's see the continuity checklist, and then we'll go to the graph, and then we'll come back to the checklist again to match this. Okay. All right. So if a function, or rather if we're trying to see if a function is continuous at a given point, all the three conditions have to be satisfied. The first one is you need to have a defined value at that particular point. You need to have a defined value at that particular point where you are looking for the continuity. You need to have a defined value there. There can't be a continuous function where at a point, where there is no defined value at that point. Okay. Next one is limit has to exist when x approaches that particular point. And last but not the least, as we have seen from the definition, the limit at that point has to be equal to the functional value. Oh, as you can see in the brackets, the value of f equals the limit of f at a. Okay. All right. Now let's see this graph and see if we can find, or rather see if the conditions are met. if the conditions are satisfied. Okay, now let's say I'm trying to find whether the function, whatever it is continuous at 1, at x equals 1. Can you just eyeball it and say whether it's continuous or not? And what's the reason behind it? Anyone?
Wouldn't it be no? It's not because there's that dot there. So it's not
Oh.
defined.
Would you please say just a little bit louder, maybe?
Oh yeah.
Sure.
Wouldn't it be undefined at 1 since there's a dot there?
So do you have, do we have continuity at x equals 1?
No.
Okay, very good. Yeah, you're right. So since you can see there is a hole at x equals 1, and there is not really a defined value at 1. Okay, there is not really a defined value at 1, right? So we say that the function is unfortunately not continuous at x equals 1. Okay, now, okay, next, let's try x equals 2. What's the answer now?
It's not continuous
And why?
because there's a hole at 2.
Okay, and what are the other things you need to check? First of all, we need to see there is a defined value or not at a. I can see a defined value at x equals 2. Can you see that? There you go. There is a defined value here. Do you agree? Although there is a hole here, but at x equals 2, I can see a defined value. That's the first category, by the way. I'm just going one by one. The first one is there a defined value at a? And the answer is yes. I have a defined value here, right?
Yes, sir.
And the next one is if the limit exists. Okay, let's try. And again, a quick question. How do you find if a limit exists at a point?
You check the left and right side limits.
Very good. Let's do that. So if we approach from the left towards 2, I can see the function is coming this way. So if we approach from the left, what's the left-sided limit? Anyone?
It's like 3.
Sorry?
There is approaching 1.
Oh, yeah. So the left-sided limit is 1, right? Because the function is coming this direction, and I can see it's actually heading towards this 1. So the left-sided limit is indeed 1. What happens to the right-sided limit? We are approaching from the right towards x equals 2, and the function is coming this way, right? Do you agree? Then I can say the right-sided limit is also 1. Do you agree with me? So the limit does exist because both the left-sided and right-sided limit approaches to, both the left and right-sided limit is 1. That means the limit exists. Now the next thing is, at that point, we need to have the same limiting value as the functional value. So what's the limiting value here when x tends to 2? When x tends to 2, what's the limiting value? Anyone? I've already mentioned it though, indirectly. And I'm showing it using the cursor as well.
When x tends to 2,
Yeah, when x tends to 2, what's the limit?
1.
One again.
Oh,
Yeah.
very good. Yeah, 1.
One.
Yeah. So we need to have the functional value 1 as well at a. Is it 1 at a? At 2 rather? At 2, is the functional value also 1? And the answer is no.
2.
It's 3.
3. Exactly. So we say that it's not continuous. Do you agree?
Yeah.
Any question from this so far? No questions at all? We'll actually solve, or rather check the continuity of lots of functions in the homeworks. And even when you discuss, we'll check continuity of so many problems. Hopefully we'll do a lot of problems in the discussion as well, where we check the continuity. Okay, it's one of the most basic things you will need in this course. Obviously, as you can see clearly, for continuity, for checking continuity, you also need to have the concept of limit, right? So that means it's actually going, or it's actually connected this way, so that you need to have the previous concept to move forward. If you don't have a clear concept of limit, you might be struggling to find continuity. And in future, when you will find differentiability, you will need to have the concept of continuity. So this way, you actually need to have all these concepts at the back of your head, because one requires the other. Okay. All right, so let's try, and or rather, let's see what the next theorem says. Theorem 2.9, the continuity rules. So let's say we have two functions, and both of the functions are continuous at a. Okay, we can have two functions on the same graph, right? We can draw two or even more functions on the same graph. That's not a problem. And both, let's say both the functions we have, f and g, are actually continuous at a given point. If that's the case, then we can use the following as well. So if both f and g are continuous at a, then if we add those two functions, that will also be continuous at that point a. Okay, and for that, obviously you don't need to graph it. You can just trust the theorem. Obviously you can't really graph all the functions. It will be time consuming. Yeah, if you can do that to cross check with your concept, that would be nice. If you have enough time, I'd recommend you to do that using the graphing tool. Just cross check that. Just take two functions, or if you have two functions which are continuous, already, just add those two algebraically, and whatever you get, graph that as well. And and cross-check that whether it's actually continuous at A or not. Okay, by just this continuity check. Okay, I know it will be time consuming, but this will, if you can do this for one or two problems, it will definitely make things even more clear. Same goes for the subtraction as well. If you subtract a function from the other, excuse me, that will still be continuous at that given point. Remember, for this to happen, for f minus g or f plus g to be continuous, both f and g need to be continuous in the first place. This will only be possible if the functions are already continuous. Okay, and same happens for the product as well. If you have two continuous functions, their product will also be continuous at that point. Okay, if you have two continuous functions where the denominator, the functional value of the denominator is not zero, then their ratio is also going to be continuous. Okay, obviously, since we know for a rational function, for a fraction, the denominator can't be zero. So at that point, if the denominator is not zero, the functional value is not zero, then we can say that the ratio is also continuous. Okay. If you have a continuous function at A, if you multiply it by anything constant, let's say if you multiply that function by 10, it will still be continuous at that function, at that point. The C signifies any constant. If you multiply any continuous function by a constant, it will still be continuous at that point. And same goes for the upgradation as well. So if you have a continuous function, if you upgrade it to any power, any exponent, any positive exponent, of course, okay, and not really positive, it has to be a whole number as well. It has to be a positive whole number. Then this function will still be continuous at A. Okay. All right. Any question from this? Although we have just seen the theorem, not really examples of it, because we'll actually use this in future. You will see we will be using this theorem for finding continuity of many functions. All right. Let's see what we have. Yeah, I think we have still time to go for this next theorem, which is 2.10. So theorem 2.10 says a polynomial function is continuous for all x. Now, why is that? Let me show a really good example of it. I have a really good one. Here you go. This is a polynomial, right? This is a polynomial. So any polynomial actually has a graph like this. By this, I don't mean this shape. I mean there is no hole for any of the x. So no polynomial actually has hole in its for any value of x. When you graph it, you'll see a graph which looks unending. I mean, you'll not see any undefined place for any x. Okay, yeah, look at this one as well. This is a polynomial again, and you can see it goes on and on. There is no break, there is no hole. So any polynomial actually works like this. And you can clearly imagine why is that. Because for a polynomial, if you remember from the algebra class or from the pre-calc, I don't remember which one it is, the domain of a polynomial is all real numbers. That means for all the x from the real number line, your polynomial is defined. So there can't be any hole, can it? It can't contain any hole. So it's continuous. Any polynomial is continuous for all x. Okay. And the next one is a rational function. That means a function of the form p over q is continuous for all the x where the denominator is not 0. And why is that? Again, we let's see one example of it. Yeah, here you go. So you can see the denominator is 0 for plus and minus 1, right? Let's look at the requirement first. It's continuous whenever the denominator is not 0. And we can see the denominator is 0 for only 1 and negative 1. So at 1 and negative 1, you can see there is a break or there is a discontinuity. Apart from that, everywhere else you can see it's continuous. It's going on and on. It's going on this direction. It's going on this direction. So it's continuous everywhere else. It's just not continuous at these 2 points, because for these 2 points, our denominator becomes 0. It will be true for any fraction, any rational function where both p and q are polynomials. If the denominator is not 0, obviously for some values, when you are working with a fraction, definitely for some values, I shouldn't say definitely, yeah. In most cases, you will see some, for some values, the denominator will be 0. And only at those places rather, the function will not be continuous. Apart from that, the function will be continuous. You will see some exceptional cases where for all the values of x, the denominator will be non-zero. So in those cases, the rational function will be continuous everywhere. I can give you one really good example of it. What if I say that denominator is x squared plus 1? Then for which value your denominator can become 0? Can you find one? Can you find any value of x which makes x squared plus 1, for which x squared plus 1 will be 0? And the answer is no, because x squared plus 1, if you solve it for x, it will give you imaginary number, right? So that means for all real number, the denominator will be non-zero. So with that denominator, whatever the numerator is, that rational function will be continuous everywhere. So for most cases, I know you will find some values of x for which the denominator will become 0, but there are some exceptions as well. Okay, any questions from this? No questions at all? Perfect. So let's end it here. So we are going to have our exam on Tuesday, and I'll make a detailed announcement about it. Hopefully I can setting up the question tonight. If not, I'll definitely do it tomorrow. And once I do that, I'll have the detailed information, how many questions are there, or if any other instructions you need to follow and all that. Obviously, it will cover from 2.1 to 2.5. 2.6 will not be included. No worries about this. The exam will be on Tuesday. That's for sure. And what else? Yeah, I think I'll have it in the announcement. So keep an eye on the announcements. And I hope you have a really, really good long weekend. Okay, I'll see you on Tuesday.
Yeah, I have a question.
Yeah, sure.
So